Today's subject is the retrosynthetic analysis of this nice target molecule, rather complicated bicyclic system with lots of functionality, an alcohol functionality, a nitro group, and an additional carbonyl group. In the background, you see a cyclohexane moiety. Well, as the first idea for a retrosynthetic analysis, we could say, let us introduce this three-membered carbon chain to the five-membered ring, and that would lead us to this starting material. And in addition, for instance, to the simple 1,3-dibromopropane. Okay, first step we would like to achieve is introducing a CC bond between this carbon and maybe that carbon, and in the second step, another CC bond formation from that carbon to the carbonyl carbon. So we would try to deprotonate here, and then we would notice this is the first problem, because alpha to this carbonyl group is not the most acidic proton. The most acidic proton is here. So we would face a selectivity problem. If we manage somehow to avoid this selectivity problem and we would achieve this CC bond formation, then we would have to change the bromide into a Grignard reagent and hope for the reaction of the Grignard intramolecular with that carbonyl group. But why should it do so? Forming the six-membered ring, maybe even better, it would go for the five-membered ring attacking this carbonyl group. And if we would think about, well, let's introduce protecting groups, for instance, acetals, well, how could we achieve the right selectivity for that? Step by step, with this idea, we would run into selectivity problems, and retrosynthetic analysis means looking for a simple solution, and with all those selectivity problems, it could not become simple. So that means this is not a good idea. Skip that, and we should go back to the target molecule and think about where are the most functional groups. Okay, here an OH group, there the nitro group, and OH better to a nitro group in an alkyl moiety means it could be synthesized by an aldol, nitroaldol addition reaction, the so-called Henry reaction. So let us therefore break this strategic bond, and this would lead us to the following structure. Let's go for the synthon. Let's say we have an acceptor reactivity here. Donator reactivity there. The phenyl group is missing. Next step, let us break this bond. Then, oh well, let's do it like that. Let's break it heterodytically, and of course here donator reactivity, because it's a natural reactivity alpha to the carbonyl, and on the other hand we should have acceptor reactivity here. So now from these two synthons, let us think about the synthetic equivalents we would need, and these synthetic equivalents should exhibit the reactivity we are in need of. So, very simple. It is just cyclohexane dione on the one hand, and this nitroolefine on the other hand, because we have donator reactivity alpha to the carbonyl, or it doesn't matter, either this or that carbonyl, acceptor reactivity here at that carbonyl. We have acceptor reactivity at the beta position of the alpha-beta unsaturated nitro compound, and we will have donator reactivity here. So, what are the reaction conditions? So, in the first step, simply those two in ethanol with sodium ethanolate as the base, it would be deprotonated here. First step would deliver this anion deprotonating here, and this is the Michael addition reaction. Then we have the anion in close proximity to this carbonyl group. Selectivity, no problem, because attacking that carbonyl group would lead to a four-membered ring. This is, of course, disfavored compared to the formation of a five-membered ring. Oh, and simply the nucleophilic attack here and protonating afterwards, that is the so-called Henry reaction. So with these considerations, we were able to develop a simple plan for synthesizing this molecule in one step from these two compounds, and you will find an easy solution how to synthesize an alpha-beta unsaturated nitro compound. Well, of course, by a nitroaldol condensation starting with nithromethane and benzene aldehyde. Thank you for listening.